Swayam Prabha. Digital India. Educated India.
With that, our complete single physics modules will be covered. So we have looked at all aspects of physics that we can model, and from that point onwards we will go on to multiphysics, that is coupling to physics. We are getting in depth into solid mechanics because solid mechanics interfaces with other physical models, for example heat transfer and mechanics, fluid motion and mechanics. You could have electromagnetism with solid mechanics or electrochemistry with solid mechanics. So solid mechanics is the science of how these elastic bodies would behave under application of external loads or forces. Okay. So far in these 6 lectures for solid mechanics, we have covered the aspects of the displacement with strain relation, forces with stress relation. We have also looked at how these stresses and strains are related using constitutive models, and we have brought everything together by the understanding of the conservation of linear momentum, that is force equals to mass times acceleration. From all of these, we then moved on to some example sets of how we can apply these concepts, looking into membranes first. From membranes, in the last lecture we have looked in the cases of thicker membranes, that is plates or beams. So in this case we have also introduced the concept of energy based analysis rather than force based analysis, and seen how we can find the Lagrange or the Euler-Lagrange equation, and using the Hamilton's principle how we can minimize the energy and get the form of the unsteady state displacement equation for the case of thicker plates, or that is plates and beams. Okay, so for this lectures, and this is the last segment for the solid mechanics before we move to the next physics, we will try to cover the elastic plates. Then we will take up some numerical problems and some analytical problems for these beams and plates. We have already covered the analytical ones for the membranes. If you look up in the segments for the solid mechanics 4 and 5, you can see the examples for the membranes with uniform load and with concentrated load. In this case we will look in the case of beams, and then we will look at some numerical applications for these. So those would be important. In the first 4 or 5 lectures we have covered these concepts of applying the numerical methods. So we can use now those methods into application for these equations. All right. At the end of this lecture we will get into the concepts of failure in materials, how a material would fail beyond the yield point in the case of ductile material, how a material would fracture, and so on. Okay. So we will get into the concept of elastic plates first. So we are carrying over from our last segment. So elastic plates, so these are 2-dimensional beams, and our beam equation that we derived from the Hamilton's principle would be used. What did we get? It is rho h of del square W by del T square minus some tension in the body into del square W plus the flexural rigidity into del 4 W will be equals to some forcing term, okay, which is a function of x and time. Okay. So this is our acceleration. So inertia. This is due to the stretching or the pretension in the body. This is due to bending, and this is the external stimulus. So an external stimulus can be pressure, a load being applied on a plate causing it to bend, that could be your external stimulus. It can be uniform, it can be distributed, it can be concentrated. We will take some examples of uniform load and for concentrated load. Okay. right. So, we can normalize this equation. We are normalizing x by L, that is the length dimension. If it has radius, then r. We are normalizing, let us not normalize w for now, that is our displacement. If you know the maximum displacement, you can normalize w with displacement. For now, let us leave it out. We are normalizing the y dimension again with L, right. Then our time will be equals to t over L square, square root d over rho h. If you substitute everything in this, you will find out this is del square w by del t bar square minus alpha of some normalized del bar square w. This is not vector, this is just normalized quantity, plus del to the power of 4 of w goes to some f, which is a normalized force or normalized external stimulus. What is this alpha? This alpha term is you bringing your d term and dividing everything with this d term. You will have it is minus t L to the power of 2 over t. So, this is your alpha, and this is some reference to the pretension or some stretch in the plate before you start your forces or before you apply your forces. Okay. So, this is our elastic equation that we get. What is this d? The d is your flexural rigidity. It is slightly different from the flexural rigidity in the case of beams. In the beams, it was E into I, where E was elastic modulus and I was area moment of inertia. In this case, since it is two dimensional, so we need to consider the Poisson's ratio, and therefore, it is 2 h cube into E over 3 1 minus nu square, where h is the thickness of the plate. So, h is the thickness or the thickness dimension in the z dimension. Okay. So, this is our elastic plate. Elastic plates, it could be circular, and then you could have it fixed at the outer edges, right. So, you will have, this is your z dimension, this is your r dimension, so r and z, and then you can apply forces on this plate, and the plate would deform and it would oscillate under the action of the force. Okay. All right. Now, we will take up some analytical problems with beams and plates. We have already covered for membranes. So, let us take it for a beam and for a plate. So, we are taking a cantilever. So, what is a cantilever? You have a fixed wall and you have this extended beam like a fin, okay, and you can apply a load on this. Okay. So, this is our beam, it's called also cantilever, and it will bend. So, this end is free and this end is fixed. Now, you can have different conditions, right. These are beams. A beam that is fixed from one end and free from the other end, that is a cantilever, right. You could have beams that is simply supported from two ends, that is they have hinges, and you could have beam that is fixed from two ends, a beam that is pinned from one end and free from the other end, and so on. So, we have looked at all of those boundary conditions. You can see that this is a fourth order differential equation. So, we need 4 boundary conditions. All of these boundary conditions we have seen in the last lecture. So, I would ask you to refer to the last lecture and look at all the different types of boundary conditions that can exist. Okay, but we are considering this case. Let us take our so rho times A del square u by del t square minus t del square u by del x square plus del square by del x square of E I del square u by del x square is equals to some force in term along x and t. This was our equation for a beam. Okay, and we had normalized this equation such that x bar was equals to x over L, right, and if you substitute this, and then t bar was in terms of E I and rho A. So, just like last case, it was square root of d over rho h. In this case, t bar will be equals to t over L square E I over rho A. Okay, that will be your time parameter. And if you normalize these, you will get d square u by dt bar square minus some alpha term d square u by dx bar square plus d4 u not u bar d4 u, we have not normalized u, by dx bar 4 is equals to some forcing term, where this forcing term into L4 over EI is equals to some capital F. Okay. Now, let us assume steady state and no pretension in the cantilever. So, we have this first term is 0, alpha is 0. So, del square u by del t square is 0, alpha is 0, and our equation therefore will boil down to del 4 u by del x 4 bar will be equals to some p which is capital P L 4 over E I. A capital P is the pressure acting on the cantilever. It is a uniformly distributed pressure which is acting on the cantilever. Okay. So, we are solving for this. This is a fourth order derivative. We will need 4 boundary conditions. So, our boundary conditions will be, so it is fixed at the left end. So, this is x bar equals to 0 and this is x bar equals to 1. So, boundary conditions will be that u of 0 will be equals to du by dx of 0 will be equals to 0, that is your fixed condition. And then for free condition, d square u by dx square of 0 equals to d cube u by dx cube of 0 is equals of 1 both of 1 will be equals to, that is your free condition, the free end. So, you have a fixed end and you have a free end. Now, if you integrate this 4 times, and the equation that you will get from here will be equals to u of x will be equals to minus p x 4 x bar by 24 plus some c 0 of x bar cube by 6 plus c 1 of x bar square by 2 plus c 2 of x bar plus c 3. Okay. On putting the boundary conditions or on applying the boundary conditions, what we will get is that u of x bar will be equals to minus p x square x bar square by 2 x bar square by 12 minus x by 3 x bar by 3 plus 1 by 2. Okay, and if we renormalize everything, then u of x will be equals to minus p L 4 over 2 E I, x bar is x over L square, we have 1 by 12 of x over L square minus 1 by 3 of x over L plus 1 by 2, and this is our equation for the cantilever. Okay. You can find out that the maximum displacement for this will be when x is equals to L. So, when x is equals to L, then it is 1 by 12 minus 1 by 3 plus 1 by 2, and you can solve this value out and find out what is, and again the displacement is negative because it is being pushed downwards, right. So, since it is pushed downwards, so the displacement is negative. Okay. Now, let us consider the same case, but with a concentrated load. Okay. So, the concentrated load case is that you have this cantilever and you have a point load, this is your x dimension, and you have some x is equals to x naught, you have a point load of magnitude 1, and you remember your old function, that was your Dirac delta function, right. Okay. Now, we have used the function from membranes, that was from membranes. We had this d squared g by dx squared plus del of x minus x 0 was equals to 0, right. This g was our Green's function, could also be replaced by u, that was our displacement. We have seen that for this variable distributed load, we had used two equations, the g equation just for the unit point load, and then p of x for the distributed point load, again refer to the last lecture. In the case of beams, for a beam, our equation will be del 4 u by del x 4 minus del of x minus x 0 is equals to 0. Why is there a minus over here and a plus over here? If we go back a few slides, we can see that our fourth order is equals to the force and our second order term has a minus term. Right. So, if we take everything to the right hand side, then the second order term will be added to the force and the fourth order term will be subtracted from the force. Therefore, our fourth order term is subtracted from the force term. This is our forcing term, and this is our bending term. We are again considering, we are again assuming one, that is steady state, and 2, that alpha equals to 0 or no pretension. Okay. So, there is no pretension in the beam. With that, now let us try to solve this. Again, delta has the property that that delta at x minus x 0 is equals to 1 when x is equals to x 0 and 0 for x naught equals to x 0. Okay. Let us try to solve this with our boundary conditions. So, we need again 4 boundary conditions. To solve this, again boundary conditions are that u of 0 equals to d by du by dx of 0 equals to d square u by dx square of 1 equals to d cube u by dx cube of 1 is equals to 0. Okay. So, again this was our fixed condition and this is our free condition. Okay. So, fixed and free boundary conditions. Okay. Now, if we integrate our equation 4 times for all x values except for x is equals to x naught. So, integrate from domain 0 to 1 except x is equals to x naught. Okay, our domain is again 0 to 1, please remember. Unlike last time in the case of membranes, it was from minus 1/2 to plus 1/2, in this case it is between 0 to 1. Okay. All right. So, what we will get is u of x is equals to a naught x cube plus a 1 x square plus a 2 x plus a 3. This is between 0 to x naught, not including x naught, and b naught x cube plus b 1 x square plus b 2 x plus b 3. This is between x naught and 1. Okay. We can put all our boundary conditions, that is we have 4 boundary conditions, we have 8 variables. Right. So, let us first satisfy 4 constants out of these, 2 constants from the first equation and 2 constants from the second equation, and we get applying our boundary conditions. We will get u of x is equals to a naught into x cube, a 1 into x square, b 2 into x, b 3. This is from 0 to x naught and this is from x naught to 1. Okay. Now, we are down to 4 constants. So, we need 4 more equations to satisfy. So, what we can do is we can consider the continuity. At x is equals to x naught. So, for continuity you will have at x naught minus should be equals to u at x naught plus, first order derivative at x naught minus equals to first order derivative at x naught plus, second order derivative at x naught minus equals to second order derivative at x naught plus, and if we integrate our equation, our governing equation at x is equals to x naught, we will get this is our integration of d4 u by dx4 minus del x minus x naught from x naught minus to x naught plus at this x naught dx. This is equals to integration of 0, that is 0. We will get that u triple prime of x naught plus minus u triple prime of x naught minus is equals to 1. Okay. So, now we have 1, 2, 3 and 4 conditions that are available. So, with these 4 conditions, so we can then substitute these 4 conditions. We can get u of x therefore, is equals to minus x square over 2 x naught minus x by 3 and minus x naught square over 2 x minus x naught by 3. This is from the domain of 0 to x naught, this is from the domain of x naught to 1. Okay. So, this is what we have for u of x. We are considering a unit point load at x is equals to x naught. If it is not a unit point load, if it has a magnitude, then you can just multiply this with the magnitude of the force and you can get a response out of it, right. So, where will you multiply? You will multiply with this del x naught term, whatever is the force magnitude, and then you can apply all your boundary conditions again and you can find the solution. That makes sense? Okay. Then we look at the case of a circular plate and could be modeled using our plate equation. So, our plate equation was rho h del square w by del t square minus some tension T del square of w plus a flexural rigidity del 4 of w was equals to some forcing term. When we for a circular plate, we consider the polar coordinate that is r theta z. Accordingly, our Laplacian and our fourth order derivatives will likewise get updated. So, del square will be 1 by r del by del r of r del by del r, and del 4 will be del square into del square, that will be 1 by r del by del r of r del by del r of 1 by r del by del r of r del by del r. Okay. So, it will be Laplacian of Laplacian. Okay. That makes sense. So, we are taking derivative of derivative. All right. Now, if we write the normalized equation for it. So, this is the normalized equation, and I am not going to normalize it again. We are doing again x is with respect to r, or r bar is rather r over r, since we are doing with respect to radius now, and likewise. So, you will have your del 4 w will be equals to some normalized pressure P. So, you have this plate, circular plate, which is fixed and has some depth, of course, and it is fixed at the ends. It has a radius of capital R, right, and you are applying a uniform pressure P on the surface. Okay. So, this is our equation. We need again no pretension, that is alpha equals to 0 and steady state. So, all of these analysis we are doing for steady state. I will give you 1 or 2 problems. I will just represent one problem for a membrane and one problem for a plate with a transient condition. Okay, just to show how you can do that. In most of these applications, you are going to use numerical methods to solve it. So, I will show an example of an equivalent numerical method for those. Okay. So, let us get back to our problem. Our boundary conditions. will be that it will be, so two boundary conditions, that it will be symmetric at r equals to 0 and u at r equals to r should be equals to 0, that it is a fixed condition. And the second one will be that the del u by del r again at r equals to r will be equals to 0, is equals to 0. Okay. Well, in this case r bar equals to 1, so r bar equals to 1, the normalized radius. All right. So, if we integrate this 4 times, what we will get, w as a function of r bar will be equals to p r bar 4 over 64 plus C 1 plus C 2 r bar square plus C 3 of log of r bar plus C 4 of r bar square log of r bar. Okay. Now, from the symmetry conditions we can get rid of, so C 3 equals to C 4 equals to 0 from the radial symmetry, and from the first two boundary conditions we can get rid of the C 1 and C 2, and our equation W will therefore be equals to P by 64 of r square minus 1 whole square, which is equals to P by 64, or in terms of capital P, that is P L 4 by D of r over capital R square minus 1 whole square. Okay. So, this is how the displacement will occur. It is going to bend inwards, it is going to bend inwards. You could consider this is an absolute displacement, it will of course will be negative in sign, it is going to slug in, and therefore, and if there is transiently it is going to oscillate back and forth. So, the second order derivative, it is a wave equation, and since it is a wave equation, it is not going to diffuse and come to a steady state, it is going to oscillate back and forth about some mean location. Okay. Now, let us look at the conditions of transiency, right. So, we have been talking about steady state all along. You would think most systems are steady state, that is not true. Systems take some time to reach steady state. It depends upon how the wave propagates, what is the wave velocity within that medium. Typically, it is very fast. So, if you are looking at transiency, those are at the very early instances, or if you are applying or the force that you are applying is oscillating, in that case you need to consider the effects of transiency. Otherwise, you can just ignore transiency and consider steady state. For most stress analysis, we consider steady state. Okay. But if you do take into account for this transient solution, then we take the case of a string. So, we have a string which is a one dimensional membrane fixed between x is equals to 0 and x is equals to 1. What we are doing, we are saying that initially the string is making some shape like this, say some arbitrary shape, and then when you release it, it starts to oscillate back and forth. Okay. So, our equation, our governing equation will be del square u by del t square equals to c square del square u by del x square, okay, where c is speed of the wave within the medium, right. In terms of tension and other parameters, you could find the equivalent from the density, and from the pretension you could find the equivalent, right. So, but the equation will be del square u by del t square equals to c square del square u by del x square. Okay. Now, we need some initial and boundary conditions. What we will have is u of x comma 0 is equals to say sin pi x. Okay. So, it will form a sine function, and then you have u dot at x comma 0. So, you need two initial conditions is equals to 0. So, your velocity, initial velocity is 0, and the initial shape of the string is a sine function between 0 and pi. Then your boundary conditions, you need two boundary conditions, that is u at 0 comma t equals to u at 1 comma t is equals to 0, that is it is fixed at both ends. Okay. So, there is no displacement at the two edges. All right. Now, to solve this, we follow the same old strategy of separation of variables or variable separable. So, we say that u of x comma t is x of x and t of t, Okay. We substitute this into our governing equation. We will have x d square t by dt square equals to c square t d square x by dx square. We can then make some replacement. We bring c square t over here and x over here, where 1 squared c square t d square t by dt square equals to 1 by x d square x by dx square. This is we take as minus lambda. Okay. If you remember, we have been taking this minus lambda or minus lambda square. You can take minus lambda square for the diffusion equation as well when we were doing heat and mass transfer, and that was because the solution for this is going to explode otherwise. You will have a sine hyperbolic cos hyperbolic dependence rather than a sine cos dependence. So, you will not have an oscillating behavior like a wave should behave, but something very different. So, we take minus lambda square in this case. Therefore, we have two equations. The first equation will be your time equation, d square t by dt square plus lambda square c square t is equals to 0, and we will have d square x by dx square plus lambda square x is equals to 0. Okay. Now, we try to solve this. First solving for x, we will get x of x just like last time is a cos lambda x plus b sin lambda x. Okay. We put our boundary conditions. We get x of 0 equals to a equals to 0 and x of 1 equals to b sin lambda equals to 0. Now, either b can be 0, that is a primitive solution, then the entire equation becomes 0, your u will be equals to 0, or we can have the sin lambda equals to 0, that is your eigen values, and the eigen solution will be lambda n equals to n pi, where n belongs to 1 to infinity. Okay. All right. Now, we therefore have this condition. Let's write our x of x, which will be summation n equals to 1 to infinity b n of sine of n pi x. For our time equation, d square t by dt square plus c square lambda square t was equals to 0. We would get t of t will be equals to some e of cos c lambda t plus f of sine c lambda t. Okay. And we know what lambda is. So, therefore, we can put everything together at u x t is summation n is equals to 1 to infinity. You multiply b n with e and b n with f. Let us write that as a n of cos c into n pi into t plus b n into psi c into n pi into t sine of n pi into x. Okay. Now, we can substitute our initial conditions. So, put initial conditions. First initial condition was that u of all x at 0, this summation n is equals to 1 to infinity. If it is 0, sine terms goes away, you have your a n, cos term becomes 1, sine of n pi x is equals to sine of pi x. Okay. If this is the case, then we can find that a n is equals to 1. So, a n is found. Now, what about b n? Then we can find that u dot of x comma 0, this will be equals to, if you take this will n equals to 1 to infinity, this will be minus n pi c of sine plus b n of n pi c of cos. Sine term goes away, cos term remains. So, we have b n into n pi c, cos is 1 and then sin pi x, this is equals to 0. Now, sine cannot be 0 for all x values, right. It can only be 0 at this at 0, pi, 2 pi, 4 pi and so on. It cannot be 0 everywhere. If that is n pi c cannot be 0 everywhere, n can be 0, in that case it is fine, otherwise it is not 0. So, what can be the case? The only case as an outcome will be that b n is equals to 0. Okay. With all of this together, we can say that u of x of t is summation n is equals to 1 to infinity, a n is 1. So, we will be left with cos of n pi c t sin of n pi x. Okay, this is our equation, and our derivative u dot x comma t will be equals to minus summation n is equals to 1 to infinity. We are taking a time derivative. So, n pi c sin of n pi c t sin of n pi x. Okay, so, this is our velocity. So, we can see that the maximum velocity mod of u dot max, which is equals to n pi c times mod of u max. So, the maximum value for this should be 1, maximum value for apart from n pi c should be 1, and if you take the mod value, and our velocity and displacement are 90 degrees phase shifted. They are phase shifted by 90 degrees. There is a minus 1 sign, and this sign has, the cos has become sin. So, it is 90 degree phase shifted, and the maximum value of the velocity is n pi c times the maximum value of this of the displacement. Okay, that makes sense. Then we will go into the transient analytical solutions for the beam. So, for the beam case, you will have del square u by del t square equals to minus some alpha square del 4 u by del x 4. Again, we are considering that there is no pretension. Our initial conditions will be that u of x comma 0 is some function f of x, and u dot x comma 0 will be some function of g of x. Okay. We need 4 boundary conditions. We can consider simply supported. So, simply supported means that u and the first and the second derivative, they are equals to 0. So, if that is the case, then u of 0 comma t equals to u double prime of 0 comma t equals to u 1 comma t equals to u double prime of 1 comma t equals to 0. That is pinned at 2 ends, and it is pin can rotate, therefore, but it is fixed to displace. Okay, so, the first second derivative is 0. If you solve this again with separation of variables, and I am doing this quickly, I want you to try this t of t. You will find out 2 equations, del square t by del t square plus lambda square alpha square t equals to 0, and del 4 x by del x 4 plus lambda square x equals to 0. From this, we can find t is equals to a of cos alpha lambda t plus b sin alpha lambda t. From this, we can find x is equals to c cos root lambda x d sin root lambda x plus e cos hyperbolic root lambda x plus f sin hyperbolic root lambda x. These are our variables and our constants. Now, let us first try our boundary conditions. So, boundary conditions, let us put x is equals to 0 is 0 and give c plus e, and x double prime of 0, it will just be the same equation, but with a minus lambda sign multiplied with it, will be equals to minus c lambda plus e lambda equals to 0. So, the cos will become cos again with the minus lambda, sin will be sin again with the minus lambda, and this will be unaffected, just lambda will be multiplied. Okay. If we compare both of them, this gives us that as e minus c equals to 0. If both of this is true, then c is equals to e is equals to 0, just the first case. Then for the second case, x of 1, we can find that is d sin root lambda plus f sin root lambda sin hyperbolic, right, sin hyperbolic of root lambda equals to 0, and x double prime of 1 is lambda times minus d sine root lambda minus f plus f sine hyperbolic of root lambda is equals to 0. Okay. Just like the last time, what we can get as an outcome from this is that d sine root lambda is equals to 0 and f of sine hyperbolic of root lambda is equals to 0. Okay. From this, since sine hyperbolic functions, it can be 0, it cannot be 0 except for x is equals to 1. Sine hyperbolic is exponential of x minus exponential of minus x by 2. So, only for x is equals to 0 this becomes 0, otherwise it is not 0. Sine functions on the other hand can be 0 over multiple occurrence, right. So, since it is only 0 at a certain location, f is 0. In this case, if d also becomes 0, then the entire solution becomes 0, that is a primitive solution. So, we can say that root lambda is equals to n pi lambda n, where n belongs to 1 to infinity, or lambda n is equals to n square pi square. Okay. Now, we can assimilate everything together and you can find u x comma t, therefore, is equals to summation n equals to 1 to infinity. We have a n cos of n square pi square lambda square t plus b n sin of n square pi square lambda square t, and then what is left is the sine of n pi x. Okay, that makes sense. All right. Now, we need to find this a n and b n. We know from our initial conditions that u at x at 0, if you put x is equals to sine term goes away, cos term remains, summation n equals to 1 to infinity, a n cos term is 1 and sine of n pi x is equals to some f of x. Using inverse Fourier series, we can find a n is equals to 2 integration 0 to 1 f of x sine of n pi x dx, and u dot of x comma 0 will be equals to summation n equals to 1 to infinity. The sine term goes away. So, we have b n n square pi square alpha square sine of n pi x, and this is equals to some g of x. Again using inverse Fourier series, b n equals to 2 over this n square pi square alpha square integration from 0 to 1 g x sine of n pi x dx. So, once you can find a n and b n for each n value, then you can find out the net u or the net displacement. Okay. We have gone over the cases for the beams and for the membrane. We have seen how to solve this analytically. Now, let us try to put it up numerically. So, for a numerical solution, this is for a membrane. So, we are considering a 2-dimensional membrane. It is a circular membrane which is fixed at both ends. This is a circular membrane. This is your r equals to 0 to some surface r equals to 1, right. It is symmetric. Our differential equation that we are using is this, that is written over here, that is del square u by del t square plus c square of del square u by del r square plus 1 by r del u by del r equals to 0. This should be minus over here, I am sorry. Okay. So, we are trying to solve this expression. Taking it to the right hand side, we can solve this. Now, numerically when we try to solve this, this can be differentiated as u of n plus 2 at I minus 2 of u of n plus 1 at I plus u of n at I divided by delta t square. This is the second order derivative. Please refer to the lectures 4 and 5 in which we have covered the numerical techniques. Second order derivatives and first order derivatives have been covered in that. So, this is the second order derivative from the Newton's method. This is equals to c square. Then this second order derivative becomes u Now at what time step are you taking? This at the n plus 1th time step, I plus 1 at I minus 1 by delta r square plus 1 by r I into u at n plus 1 I plus 1 minus u at n plus 1 I minus 1 by 2 delta r. Okay, so this becomes your governing equation. Now we are trying to solve this governing equation. What we need are the initial conditions. The initial conditions, we can say that this membrane is initially flat. That's what our initial condition is. It's initially flat, and that we have no velocity. We also consider that there is a driving pressure force to this. So we can go back and we can add a pressure force term. So this is P naught. Okay, so this is our driving pressure force, driving stimulus. Right, and it is acting on this P naught. Okay, so we have this membrane which is connected and we are pushing it down onto the surface. All right. So what is our requirement? This is our requirement. Again, if I can draw this for this case. So this is our matrix for U. Okay, this is your r dimension, this is your t dimension. For that first time step and second time steps will be driven by our initial conditions. So first time step we know that u for all r values at the first time step is equals to 0, and del u by del t at the first times t equals to 0 is 0. So u at all rows at 2 is equals to u at all rows at 1. Okay, so now by now you should be familiar with these, with the different boundary conditions, right? If it is a 0, that means that u2 minus u1 by delta t is 0, and therefore u2 is equals to u1. Okay, so you have now a full information of these first 2 rows. Now for the next row onwards, you will start your oscillation using the data for the last step. So for n plus 2 is what we want to find. We know the information for n plus 1 and n, and we can take everything to the right. All right. Our boundary conditions are again fixed. So these are our initial conditions. Let's write. Our boundary conditions are again fixed. So u at 1 for all time steps is equals to 0, and u for the last row, that is nr, for all time steps is equals to 0. That is fixed at both ends. Now that is not the case for this membrane. In this case, since it is circular and it is symmetric at the center, our boundary condition will change, and that is del u by del r is equals to 0 at r equals to 0. So u1 will be equals to u2. Why is this? This is because it is circular symmetric. Had it been a string, one dimensional, then it would have been fine. But since it is not a string, it is a circular membrane at the center, and when at the radius at r equals to 0, you need anything positive of r0 and negative of r0 should be symmetric. It is like a mirror image, and for that the derivative needs to be 0. So if the derivative is 0, then u1 will be equals to u2 at the center. Those boundary conditions have been put in. Over here we have taken C as 1, N as 1, dr, dt, and all everything is created. You can see this algorithm and at your leisure. Again, this is your central symmetry, and this is your fixed end, fixed outer edge, right? And you can see from this animation is that the membrane is flexing. This is your displacement u, and the displacement it exceeded and went up. Okay, so and this is the maximum displacement that you can get. Let me run the animation one more time. Again, you see that u is the displacement, right? Not xy. It's the r coordinate, and then the displacement reduced, and then the displacement again went back to 0. It exceeded 0 and it came back, and it will keep on oscillating. Gradually it will come to and the oscillations will gradually dampen out if there is a dampening factor and come to a steady state. If there is no dampening, then it will keep on oscillating. It's like a drum, right? So when you're beating a drum, you're putting a force, and that P is the force, and that is causing the drum to oscillate. So this is how the oscillations will look. All right. For the case of a beam, we can do a similar analysis. So, we are taking a beam which is simply supported. If it is simply supported, then the boundary conditions becomes that u at 0 equals to u double prime at 0 equals to u at 1 so u double prime at 1 is equals to 0. This is for a simply supported beam. And our equation is this. So, we have del square u del t square is equals to minus del 4 u by del x 4 minus some pressure P. Okay, so, minus some pressure P, and that pressure is being applied. Now, keep in mind that is a fourth order derivative. Right. So, you need to disintegrate it into a fourth order term as shown over here. So, you can see that it goes from so this derivative will go from u for a given n plus 1 I minus 2 plus 4 is minus 4 plus, let me just check that once quickly. Minus 4 of u n plus 1 at I minus 1 plus 6 u n plus 1 at I minus 4 u n plus 1 at I plus 1 and minus and plus u n plus 1 at I plus 2. So, this is your del x to the power of 4. Okay, this is your fourth order derivative. You can find these derivatives from any numerical textbook which has this numerical differentiation given, or you can look up in Google and find a PDF which shows a forward difference, backward difference for nth order derivatives using these variables. All right. So, this is what we are doing. We are simulating this. We start from time 3 just like last time. So, first time 1 it is 0. You can either take an initial profile, like you can take sin pi x, or you can take 0, or you can take any other profile. So, in this case u is equals to 0, u dot equals to some velocity, in this case velocity is taken 0, therefore, u2 is equals to u1. Okay. Then we are solving this governing equation, and we have our boundary conditions. So, u1 is 0 and u2 is equals to u1 plus u3 by 2, which you will get likewise for the two end conditions. And if you see the animation over here, yes, so you can see that this animation is slightly bending down under the applied load, then going back up, and it will oscillate a bit and will come down, and it will keep on oscillating back and forth. All right. This is how you would do a numerical application for these. Lastly, we will talk about the failure criteria, and with this we will end. So, a time dependent material response is best characterized by the incremental constitutive relations. And this is called the plasticity theory. Okay. So, if your body will come back to its original state, it is elastic, but if it has a time response, means if it is deformed and it does not come back to exactly to the original shape, and then it has some strain that is stored in the memory, and that strain would be used for the next iteration, right. So, if you have a sigma versus epsilon plot like this, then up to this point is your elastic condition sigma y, and beyond this point is your plasticity. So, if you have a point over here, you will come back following the same slope, that is E, and this will be your epsilon p, that will be your residual plasticity in the material. This phenomena is called hardening, in which the material hardens and then the material can actually come down, and that is called softening. Okay, so this is the behavior for a ductile material. The failure stress is typically given as sigma f is typically taken as the yield stress of the material, and there are different stress criteria that you can use for this application, right. So, the yield criteria or the yield stress is an invariant, and how is that invariant determined? That indeterminate is given by f of I1, I2 and I3, and that is your yield criteria. Any yield criteria will be given by the same, where I1 is equals to sigma 1 1, that is your hydrostatic component, I2 like 1 half II, sorry, hydrostatic component is Ij sigma Ji, and I3 equals to 1 by 3 of sigma Ij, sigma Jk, sigma Ki. Okay, so these are invariants, means that these are not affected by the transformation of the coordinate system. Okay. All right, we'll skip over a bit and we'll go to the ductile failure criteria. There are different ductile failure criteria. The simplest one is called the maximum principal stress, and under this criteria your sigma I should be less than equals to the yield stress sigma y, and this was given by Rankine. Slightly modification of it would be the maximum principal strain, and this is also called the Saint Venant's principle, in which sigma 1 minus nu times sigma 2 plus sigma 3 should be equals to sigma y. It is called Saint Venant. And then you can have your maximum shear stress. The maximum shear stress, that tau, which is equals to sigma 1 minus sigma 3 by 2, should be less than equals to the maximum shear stress or the maximum yield stress. This is called the Tresca. Okay. So, and there are two other conditions which will be based upon the total strain energy and the von Mises. All of these failure criteria, and we will go in depth when we go into fracture mechanics towards the end of this lecture series, are based upon these principal stresses sigma 1, sigma 2, sigma 3, and they can be found from the invariants, right. So, we are comparing the yield stress or some failure criteria for causing the material to fail. Now, once we have our stresses exceed this critical stress, then we say the body has failed and we can throw away the body or we can remodel the body for a different purpose. Right. So, with all of these information, we have now an understanding of how stresses and strains behave, how a force can cause deformation, and then we can get the stress state of the body. With the stress state, under these failure criteria, we can say whether the body is a safe design or not a safe design. We will come into more depth on these failure criteria when we look into the concepts of fracture mechanics and failures towards the end of the series. So, thank you so much for listening.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I am not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams, but I am also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.